Our next speaker will talk remotely. The title of his talk is Generating Generators. Please welcome Tamir Bahar.
Hello everyone, my name is Tamir Bahar. I'm here to talk to you about generating generators. Because we all trust the internet very much, my talk has been pre-recorded. Please enjoy the video. Hello everyone, my name is Tamir Bahar and I'm here to talk to you about generating generators. Now, before we begin, I want to make a single disclaimer. Right across from my home office, which you can see in the picture here, there's a construction site, which means there may be some loud noises. I did my best to keep them off the video, but I might not have been entirely successful. Additionally, construction sites tend to cause glitches in the matrix, so if you see my shirt changing randomly to a different color, it's probably because of that, and not because I'm doing multiple takes to get this right. With that in mind, let's begin. Hello, my name is Tamir Bahar, and I'm here to talk to you about generating generators. Now, before we get started with actually generating generators, I want to talk a little bit about myself. Both because I like doing that and because I think, sharing motivation is important. So let's start with that. See, I'm new to Go. I've been coding in Go for about 1 year now, and this is probably my first big project. Before learning Go, I've been coding mostly in Python and C++ for quite a few years now, and I've gotten quite used to those languages, all the high-level abstraction, and on the other hand, all the mess that they entail. You see, coming from Python and C++ to Go is not an easy task. You see, liking Go, liking Python and C++, there are a lot of features that I'm used to. Templates, decorators, exceptions, many complicated libraries and syntactic tricks that I can use everywhere. And I like doing that. Going to Go, I had to get rid of quite a bit of that, which was not easy, but after time you learn the idioms, and the first time you go into the standard library to see how something is implemented, coming from C++, it's quite a shock, because in Go I just went into the standard library and I could read the code, and it seemed like good, reasonable code that a normal developer would write. In C++, it's a total mess. It's truly difficult code to write. And that's a significant improvement as far as I'm concerned. Additionally, the moment I wanted to deploy some of my software or distribute it, the fact that Go comes in a single binary with no additional runtime that you have to install, that's amazing. In Python, I always have to tell people install Python, install those packages, and hope for the best. And with C++, I need to compile for a separate operating system, which is slightly more difficult than it is, very difficult in some cases, and they need to make sure they provide all the necessary third-party libraries that are often dynamic libraries that get loaded at runtime. With Go, it's a single binary, so it's truly an amazing experience in that regard. Like being able to jump into some code or just give someone a binary, that's wonderful. So as I learn more and more Go, I learn to appreciate it more, but there are still some things that bother me, some features that I'm missing. The key one among those is generators. It's a Python feature. You see, generators are basically a simple way, straightforward way to create iterators. We'll get to that more in a bit, but first, again, still talking about me, I want to talk about my workflow. See, often, as it would happen to all of us, we encounter new APIs. Those new APIs may be remote APIs via REST or GraphQL or something else, and they may be operating system APIs or some third-party library, or they may just be even in the standard library just a data structure or a function that we did not see before. And as the case is with most code, the main thing we're dealing with is data. And again, we can read documentation about the data, we can look at the code and see the structures, but at least for me, I like getting my hands dirty. I like seeing the actual data I'm working with. And since that sometimes requires work, the first thing we do when I encounter a new API is implement a simple printing function so that I can see all the data. Here, for example, we have a function that takes a library and prints all the books in a library. Yes, this is a physical library that people go to read, in not a library module or not a code library on your computer. So what's a library? I'm assuming you're all familiar with them. It's a big building, it has rooms, the rooms have shelves, the shelves have books, and then you can take the books and print them. And then we can see the actual book data and see what's going on and what do we want to do with that. Now, it's not relevant here, but generally when I write that kind of code, if there's any error that I need to handle, I just panic. So you don't want that in your actual code in production, but it's really easy afterwards when you order a factory, just look for all the calls to panic, replace them with actual error handling, and you can go ahead. If instead of that I start ignoring errors just to get my examples right, just to get the first function working, then it's very easy to forget about it. I mean, I'm not going to look for underscore everywhere, or wherever I printed an error. It's less useful, so I try to just panic. Again, you should replace all of those panics when doing something else, but let's just start now. Once we have that print function, we want to write our business logic, and then comes the question. Where do we write that actual business logic? Because you see, one option is to replace the print with the business logic. That works. But as the code grows and grows and gets maintained by more people, that's gonna be quite a mess. Also, it's not unlikely that we want the same iteration logic in multiple places in our code. One way would be to duplicate it, which in this case with a simple API, it's not that bad, but if we have to authenticate and make sure we handle the tokens correctly and a lot of error handling, that's not going to be fun. We want to put all that logic, all the iteration logic in one place. And if we put it in one place, we need to somehow get it. Now, one way would be to run all the iteration in advance, like here we get all the books in advance, return a slice and work with that. This works, but if we have a lot of data, if the data is expensive, for example a remote API which we pay for usage, we don't want to get everything. We want to stop as soon as we get what we need. So just returning a slice would not work for us. Another option other than returning a slice is getting a callback. That works, but in my experience it gets a bit messy. You need to start dealing with reporting errors and telling the function where to stop and getting all the data out. It gets the code really complicated really quickly. And also I just want, I like this structure. I have a loop, I have something in the loop, and it just works. So the next best thing you can do is use iterators. Iterators basically allow us to get our data on demand. Instead of getting an entire slice, we just get something that we can iterate over. You see, we start by calling iter books and pass in a library. Then you get an iterator object. With the iterator, we can call the next method to advance it to the next book every time. When we call next, it does everything that needs to happen in order to advance. Then it returns true if there is a value and false if there isn't. We go ahead and use the value method to actually get the value from the iterator and print it. Last but not least, when iteration is complete, we check the error method. If an error was reported during iteration, which would also stop iteration immediately, we'll get an error. If not, error would be nil. This allows us to check at the end of the iteration whether there was an error or there wasn't. In this case, we're all good. And again, remove those panics when you actually go to production. Now, iterators are wonderful, but they have one key issue. They are very, very hard to implement in Go. At least for me. Generally, they consist of 5 parts. One is the iterator structure. The iterator structure needs to hold all the state that relates to iteration. If it's a local API, it can just be a couple of indexes. If it's a remote API, it might be some authentication info. Again, the state of the iteration, maybe some other temporary data that we need to maintain. Next, we need to create the constructor, because some iteration info might not be trivial, and we don't want to bother the user with that. Then we have 2 getter methods, value and error, which we've seen before. Sorry for the typo here. We just generally implement the simple getters to get the current value and the current error. And last but not least, we have the next method that is responsible for maintaining the state of the iterator and advancing it from one state to the next one. Now let's see what it actually looks like. But before, as you can see, all those 5 things can get quite intense on the screen and we would not have place to put them. So instead, we're going to use what I call a closure iterator. This is a slight transformation of the iterator pattern we just described to actually make it fit on a screen and a single function. Instead of the 5 pieces we've seen before, we have one piece here, a function returning a closure. The function, in our case, would act just as a constructor. It takes whatever values we need and it will return the iterator we want. Next, we have a state block. The state block holds the state of the iterator instead of the struct we discussed before. All the variables we define here would be captured by the closure function and therefore would be maintained as if they were a struct. Next, we have the advance function. The advance function replaces the next function and works a bit differently. Instead of just returning a boolean, when we return from it, we return with value, reporting the value that would need to be returned from the value method, report with error, indicating the error that needs to be returned by the iteration, or alternatively, we return exhausted, indicating that the iteration is complete and there's nothing more to report. Now, let's take another look at the function we implemented before to print all the books. It's a simple, straightforward loop with a print in the middle. Now, let's look at the iterator implementation for that. That's quite a lot of code, if you ask me, and besides just being a lot of code, there are some glaring issues here that need to be addressed. First, we have some weird initialization in the beginning. We initialize an index to -1 instead of 1, just to get the indexing simpler as we go along. Then, there's some tricky indexing where we zero stuff and increment others, which again is somewhat tricky to understand and is hard to maintain. And last, but very much not least, we're suddenly working from the inside out. Instead of iterating over rooms and then shelves and then books, we're iterating over books in the current shelves, and then the shelves in the current room, and only then the rooms, which is quite an inverse way to think about stuff. Now, I don't know about you, but this was hard for me to implement. I made a lot of mistakes. I implemented it once, thought I got it right, ran the tests, it was nowhere near correct, and I had to go through quite a few iterations until I actually got the code working. Now, there may be a better way to do it in Go right now. You may know a better way to do it in Go, or maybe you're practiced in writing iterators so it's simple for you now and you know all the tricks. But it's not going to be simple for everyone. When a new programmer comes to your team and looks at that coding to make a change, yeah, they're going to make a mistake, because with this kind of code it's almost impossible not to. Additionally, converting a simple nested loop to an iterator should not be a challenge. It should not be an interview question. It should not be something that you have to think about. It should be straightforward and easy, because if the original code is easy and we know exactly what we have to do, it should not be so hard to make it work. So let's see what generators do for us. You see, if we had generators, the function to get an iterator of that would look like this. You can see we only made 3 changes here. First, instead of having no return value because we were printing, now we return a generator of books. That seems to be sensible since we're creating a generator. Next, instead of the print function, we call yield. Yield means basically that we are going to take that value and it would be available for the yield, the value method we saw before. Last but not least, when we're done, we're going to return nil because, well, after all, in Go, a function must return, if it returns a value, it must return the value from all code paths. You cannot just not return. As a bonus, we're going to use that as a way to report errors. If we had an error, instead of returning nil, we're going to return that error. Now, this looks quite straightforward to me. I mean, I can read this code, understand what it's doing. Yes, I need to know what a generator is, which we'll discuss in a moment. But looking at this code, the transformation is pretty obvious, and I'm pretty sure that you can see that we iterate correctly for everything, which in the previous code, well, I have to take some time reading this to make sure that the iteration is correct. So what are generators actually? Well, a generator is every function that uses yield. As soon as we use yield in a function, we create what is called a generator function. Generator function works slightly differently from other functions. You see, when we call a generator function, no code in the function gets executed. We return a generator, but the code, well, we don't touch it yet. Then, when we start iterating over the function, we'll see what's going to happen. First, we create the generator, and we call iter_books, and we get a return type. Then, when we call next, the function, and only when we call next, the function would start executing. We'll go through the code line by line, as if it was a regular function, until we reach the yield call. As soon as we reach yield, we return true from the next function, and continue in the original, in the caller, with our state preserved. Then, when we reach call to value, we get the value that was yielded previously. And again, no more code is executed in the generator function yet. Then when we call next again, we'll continue and run through the function line by line like a normal function until we either reach yield to yield another value, or reach a return. When we reach a return, next would return false, the iteration would stop, and we'll be able to check the error. Since we returned nil here, everything is good. Had we returned an error, that error would have been reported via the error function, and we would be able to handle it. Now, I like generators. They are amazing. As you've just seen, they take some really large piece of code that's hard to understand and convert it to something that's as straightforward and simple as printing. That's, in my opinion, absolutely wonderful. But unfortunately, they're not Go, at least not yet. If there's anyone here from the Go development team, like, I would not say no if you suggested that as a feature. I might even do it myself, but now is not the time to talk about that. So if we're not gonna change it by changing the language right now, then another thing we can do, obviously, is try to create some runtime library to do the same thing. Some languages do that, but runtime libraries have the issue of handling different architectures and different operating systems and a whole lot of mess because we're lacking context that we have in the source code. So I don't want to do it. So that I can modify the Go compiler. You should have all the information I need and be able to generate whatever I want. But I want all of you to be able to experiment with this, to be able to play with generators, to see what they can bring to your code bases, which you will be able to do at the end of this talk. Now, if I change the compiler, then sure, you can take the compiler and run some toy examples and see what happens, but generally replacing a compiler in a project, even in a wonderful language as Go that maintains backwards compatibility, is often not an entirely smooth sailing. There will be some weird issues, so if I gave you a new compiler and told you, yeah, go take your million lines of code project and just run that, it should work, you may try and it would probably fail, and then you won't experiment with it. So what I went for was code generation, which means I take your code, I process it using my tool, and give you new Go code. And then you can take that Go code and use it wherever. It's proper, correct Go code that just works. And so you can use it on toy examples, and you can use it on massive projects, just to test it in one place and see if that helps you in any way. Now, it might seem daunting, but luckily for us, Go has absolutely amazing tools for code generation. I've been using C++ and I've been using Python, and I've done some code generation in both. This is not the same level of experience. Go is absolutely phenomenal here. And this is thanks to quite a few tools that we'll discuss. First, the Go generate command. In fact, we can just put a line in the code that says, hey, for this code, if you want to generate it properly, you need to run this line. That's truly wonderful. That allows us to indicate in the source code without some messy build system around it. Then we're going to use build tags and build constraints. Yes, in other language we have some defines or macros and all sorts of stuff. In Go we just have build constraints. They allow us to specify that one file would only be built when specific build tags are present. So for generator definitions, our pretend Go code, we're going to use the gen tag as a constraint. Then when we actually generate our real Go code, we're going to use the not gen tag. So we make sure that they would never conflict, since they would still have the same names for functions and variables. And this allows us to completely separate the pretend Go code that we just saw with yield and generator from the actual Go code that would be executed, which we'll see in a moment. And the rest of the code that we're not modifying, is just going to be copied verbatim, so we're good to go. And then eventually, like I said, only the real Go code, only the things that are not pretend Go with yield and stuff, only the implementation of our generators get into the actual executable. That's really neat. In addition to that, Go has amazing tooling for parsing Go code. The standard library has type checker and has an AST. There's a package to load all the packages and parse them. This is absolutely phenomenal. The fact that you just in a few lines get the entire AST, which means abstract syntax tree of your code. You can get the types for every single variable that you see in the code. This makes parsing so much easier. But we're not going to dwell on that now. We're going to see how we actually take our existing pretend Go code and transform it into actual runnable Go code. See, the trick is to use what we'll call code transformations. We take the pretend Go and transform it into actual Go. And here we're going to start with the simplest Go generator possible, the empty generator. It yields no values and returns no errors, just return nil. So here's what we're going to do. We're going to use the closure iterator that you've seen before in the following manner. We're going to take the body of the empty function we just saw and copy it into a closure iterator. In the closure iterator, we just return nil. Again, we said we cannot return nil because we need to return a boolean, so we return exhausted, because returning nil from a generator means that we exhausted the generator. With that, we have our generator working. Next up, the next simplest one is returning an error. Again, yield no value, return an error. For that, we do the same trick. We take the body of the function, we copy it into the advanced function in a closure iterator, and then replace return my error with return with error of my error. So that we report the error that we just defined. So far, so good. Next, we're going to try and look at what happens when we actually yield values, because as fun as it is to just report errors and do nothing, we want the data. This is what we discussed. This is what we need here, actual workable data. So again, the simplest generator that yields value is a generator that yields one value and reports no errors. Now, if you're wondering, just before we start with it, the yield function does absolutely nothing. It's just a nice placeholder to make sure that things are working as they should. So let's do the same process. Take the body of the function, gen.yield hello world, return nil, and copy it into a closure iterator. So far, so good. Then we replace the yield call with return with value, because again we want to return that value for the value call method. Now, here we have an issue. We run this function once, we return with a value. Return true and yield the value. Next time we run the function, we get to return with the value again. We yield the value and return true. And we just keep iterating infinitely. That is not exactly what we want. We want to yield the value once and then exhaust the iteration. We need to do something about it. And this is where things start to get a bit more messy and also a bit more fun. See, we're going to write quite a bit of code and use quite a few interesting tricks. Before each of our lines, we're going to add a label. One at the beginning of the original function, before the yield statement, and another before, right after the yield statement. Because as we discussed before, when we start running a generator function, the first thing we do is run up until the yield. And the next time we run it, we start right after the yield and keep going. Here, you can see those two labels, label 0 right before the yield, and label 1 right after it. Then we're going to add a switch block. Switch block is going to tell us whenever we enter the function which label we need to get to. It can either be the label 0 or label 1, depending on whether it's the first or second time we enter the function. Then we're going to add a variable in the state block so that we know which state we're in. We initialize it to 0 to indicate that we start with the first line of the function, which is reasonable. And before we return with the value, we set it to 1 to indicate that the next time we go into the function, we're going to go to label 1 and exhaust the iterator. Then we replace return nil with return exhausted, and we are done. So, like I just said, we're going to be using goto. Now, I can just go ahead, but I don't think any of you would forgive me if I just said we're using goto and kept going just like that. I mean, for the last decades, goto's had a very bad reputation. Some might even say that goto is considered dangerous. Now, I'm not going to say anything about C's goto. That is, well, it's a mess, but Go has done a great job of making goto a lot safer. A bit of an issue to us, but we'll get to that in a moment. See, Go added two limitations. Go added two limitations to goto. The first one is you cannot skip variable declarations. If you have a goto that goes beyond the variable declaration, it would simply not compile. Why is that important? Think of the other case. If you can skip a variable declaration, what would be the value of that variable? Would it be initialized? To what value? And instead of starting to think about stuff like that and wondering what is going to happen, we just disallow it entirely and make sure our code is more consistent. Second thing is, gotos in Go cannot enter code blocks. Sure, we can probably reason about what happens if they do, but think about the code that you generate. If you have, for example, an if condition, and then you have the if block. If you just go straight into that block without checking the condition, the code would not know how to handle that. And sure, you can write code that does it correctly, but it's just safer and simpler to entirely disallow that. Now, since we are going to declare variables, I mean, writing regular code, and we are going to use flow control, so blocks are going to be present, we need some way to handle that, some way to take the gotos that we need, as I just showed you, and use them despite of those limitations, or improvements, as one might say. So how are we going to do that? Well, in two steps. First, let's handle variable declarations. What we're going to do is take all the variable declarations from our generator, from our iterator function, and just pop them up to the state block. And this gets us two things. One, since the state block is before the function itself, all the gotos are going to be after that, which means we never jump over a variable declaration. The second thing is, as we said, we're doing a generator when we want to maintain the state between different calls to next. By moving all the variable declarations into the state block, we guarantee that the state would be preserved, as it is captured by the closure in our closure iterator. There's one thing we need to handle. In some cases, different blocks may have the same variable names. In those cases, we'd have to rename those variables while we're generating the code. Again, luckily, the Go tools allow us to do it very smoothly. Now that we're done with variable declarations, next thing we need to discuss is blocks. You see, blocks are generally used for two things. One is variable scoping, and the other is control flow. As we've just seen before, since we take all the variables from all the scopes and put them in the state block, we've essentially eliminated variable scoping, which means the only thing that blocks do now is control flow. If we have an if condition, we have a then block and an else block. If we have a for loop, we have the block that gets repeated. But as we said before, we need to jump into those, so we need somehow to transform those blocks away as well. And this is how we're going to do it. Let's take a simple if condition to start with. We have if alpha, if it's alpha, we print A, B, C, we yield A, B, C, else we yield 1, 2, 3. Simple enough. And let's look at the control flow graph for this piece of code. We have a condition, then we either go to the then block, which is A, B, C, or the else block, which is 1, 2, 3. And once we're done, we go after the loop. Now, we're going to start adding gotos to slowly transform this into something that does not use blocks. First, we're going to add a couple of labels. They don't do anything, they just help us denote the parts that we're talking about. The then label denotes the then block, the else label denotes the else block, and the after label denotes the code after the if block. Then we'll add a couple of gotos. And they're just, again, repeating the same structure that we already had. After the then block, we jump to the after, and after the else block, we jump to after as well. Then we'll add a couple more gotos, and that again, just jump immediately to the proceeding label. They don't change the flow at all, they just help us with the next step of the transformation, which is take the code out of the blocks and just leave the goto there. So now you have the exact same control flow. You can see the gotos in the middle of the arrows, but other than that, everything is identical. But we have no code inside the blocks other than the gotos. We have if, and then we go to either the then label or the else label. Since all the yields are outside of blocks, we can use goto to get to either one of them when we need to. It allows us to complete the transformation. Next, we're going to go over some more control structures to see how to transform them to avoid blocks. The first one is the simplest loop we can have in Go, which is a forever loop, for without any conditions. The first thing we're going to do is the same step, add a couple of labels. Then, with the labels, we're going to add gotos. Now you can see that we already replicated the structure of the flow entirely without using the actual for instruction. For if you look at it, you have the loop inside here, and the for is just doing nothing, so we can get rid of it. And with that, we've implemented the forever loop. Next, we have a while loop. A while loop is a basic loop in Go, where instead of just having the for, we have for and a condition. Again, I'm using what might be considered as C terminology for the loops, because I need a name to use here. So what we're going to do is try to transform this into some structure that we already know how to transform, which means we're going to take a while loop and convert it into a forever loop and an if condition. From this point, we can just use the transformation we did before. We can transform the if and we can transform the for loop. So we just get a transformation immediately. We have the loop head and the loop body. We have a goto that jumps to the top. We have the condition handled as we did before. And that's basically it. Next, we have a C-style loop. C-style loop consists of three parts. First we have initialization, then a condition, then an increment, and of course the loop body. Now we're going to try again to transform this into some structure that we know how to handle. We move the initialization outside of the loop, just like every other variable declaration or initialization we've handled before. In the rest of the loop, we transform from a C-style loop into a while-style loop, which we've transformed a moment ago. One thing to be sure of is that if we have a continue instruction inside the loop, we need to make sure that you jump to the loop increment and not to the loop head. For if you jump to the loop head, we'll just loop indefinitely without changing the value of n. Now, once we're done with that, we can continue with the transformation we described before. N goes to be declared outside of the function in the state block, and the rest of the transformation is identical to the while loop that we discussed before. Next, we have a for range. And this is a slightly different type of loop, and we need to handle it as well. Now, since we don't have any variable here that actually indicates the state of the slice, once we use range, we just start going through it, and we need to somehow preserve that state. For that, we're going to use adapters. Use a slice adapter, basically takes a slice and converts that into an iterator. Since it's an iterator, we iterate over it like we described before. We initialize the iterator by calling slice adapter. Then we loop over it using a while loop, where we set the values of index and item, just like we do in the original loop, and then call yield. Now this, as we've seen before, this is a while loop with an initializer before it. So we can transform it using the rules that we saw before. Now that we know how to handle a slice, we also want to handle maps and channels. Now, maps behave a little bit differently. So when we create a slice adapter, all we need to do is remember the index with which we're iterating over the slice, because the slice has a fixed iteration order. When we iterate over a channel, we just need to keep getting the next item from the channel. With a map, however, the situation is a bit different. For a map, does not allow us a consistent way of iterating over the map. Each time we try to iterate, we'll get a different order of elements. Because of that, we will take the map, transform it into a slice of 2 elements each, and then start iterating over that as if it was a slice, but instead of just getting the value, we'd get the key and the value from the map. And this also means that if the map gets transformed during the iteration, we would be entirely unaware of that. Generally, it's a bad idea to transform the values you're iterating over. Now, that done. Now, there are quite a few more control flow structures in Go, and we're going to stop here and not cover all of them. Now, generally, all control flows can be transformed in a similar manner, whether it's switch or type assertions or select statements. All of them can be transformed in a similar manner by taking the code from the blocks and just putting it outside. Some of them would require adapters, some of them would require some extra work, but generally, if it makes sense, it can be modeled in this manner. And specifically, that's generally what a compiler does. Now, there's one exception to this rule, which is the defer. Now, let's say that we defer in a regular function. We defer, we execute the function, and when we exit the function, the deferred statements get executed. Now, what happens with a generator function? Because the generator starts when we call the function, but no code is executed. So there's nothing to defer yet. When we call next, we get a single execution of the function, but if we're using defer to manage resources for the generator, we only want... But if we're using defer to manage the resources of the generator, we only want them to be executed or released when we finish iteration. But what if we never do that? So defer does not make a lot of sense inside a function that keeps repeating itself and getting called over and over again. So generally what I would recommend is deferring outside of the generator and passing the initialized values to the generator once you're done handling the generator, just clean things up. And now it's time for a simple demo. You can recognize all the things you see in the screen from our previous slides. First, we have the build constraint GenGen to make sure that our code is only interpreted as pretend Go code. Then we define the package, which is natural, and import the GenGen package so that we can use generators and yield. Then we have a Go generate line to take our pretend Go code and create an actual Go file from it. And lastly, we have a Fibonacci function that generates Fibonacci numbers and yield them. Nothing special here. And then we run Go generate tags GenGen to generate our code. And we generate something that's pretty similar to this code. First, we have the not GenGen build constraint to make sure that this does not conflict with our pretend Go code. Then we define the package, import GenGen, and define our actual implementation of the generator. You can see that I've prepended underscore next, underscore to next and to the other labels. This is basically to avoid conflicting with names that already exist in the generator function. It's a lot easier to just add double underscores and be fairly sure that no one does that in their own code. Then we write a main function to use our generator function. As you can see, this function is entirely unaware of the pretend Go code. It just calls a generator function to create a generator, iterates over the generator, printing the first 10 values, because if we go too high, it's gonna get crazy, and prints them out. Run Go 1, and we get the Fibonacci numbers. Done! Thank you. Now, just one more thing before we finish. If you want to play with the code, it's already up on GitHub and on the package Go Dev. You can go ahead, download it, play with it, tell me how it's broken or how it is wonderful, whichever suits you best. I'm available both on GitHub and on Twitter as TMR232, and naturally I'll be here to talk to you now. Thank you. Hello everyone. Hope you enjoyed the talk.
As always, should you have any questions, please raise your hand and I will come to you with a mic.
Hey Damir, thank you for the talk. I do have a question. Have you considered into kind of generating a graph to actually just like move the whole flow execution of the code instead of maybe, I don't know, using GoTo and maybe making something a little bit more structured, or just like that follow data structure that somehow is used?
No, I did not consider using a graph. This solution seemed obvious to me, having had experience with assembly language in the past. So using GoTo just seemed like the obvious thing to do.
Okay, thank you very much.
Thank you.
If there are no further questions, I would say thank you again, Tamir, and well, we have the coffee break now, so enjoy yourselves.
Thank you.